Welcome to the fifth lecture of Module 2 of the course called Game Theory and Economics. Before we start this lecture, let me recapitulate what we have done in the previous lecture, lecture 4. What we have done is that in the previous lecture we have examined what is the implication of altruism in situations like prisoner's dilemma. We have already discussed the prisoner's dilemma game. Typically in a prisoner's dilemma game, the players have an equilibrium, a Nash equilibrium, where the payoffs that they get is less than what they could get if they had cooperated with each other. But they don't cooperate with each other and they try to free ride, and that's why, since everyone is trying to free ride, they are pushing themselves into a situation, an equilibrium situation nevertheless, where the payoff of each player is less compared to the case where they had not tried to free ride. So this is basically coming from the fact that people are maximizing his or her individual payoff. We have tried to relax this assumption, and we have seen that if there is altruism, what we mean by altruism is that an individual cares not only about his own payoff but also the payoff of the other player. And if that is the case, then we could get an equilibrium which is the best for everyone. That is the result that we got in the previous lecture. Typically, we saw that if the degree of altruism is high enough, if people care about the other player above a particular critical limit, then we can get that equilibrium which is the best possible outcome for everyone. But if the degree of altruism is there but it is little, then we get a prisoner's dilemma kind of situation where the equilibrium is what we call Pareto inferior compared to another outcome. We have already seen that though this situation is there, that altruism could generate an equilibrium which is Pareto optimal, that is, it is best for everyone concerned, but altruism per se is not good. I mean, there might be situations which is not like business dilemma like situation where altruism could in fact be harmful, and we have seen an example where in fact without altruism people were getting an equilibrium which is best for everyone. But if there is altruism, we get back to the prisoner's dilemma kind of situation where the equilibrium is it's an outcome where people's payoffs are less than what they could get if they had did not have altruism. So that's the main theme of the last lecture. Today what we are going to do is to consider some of the variations of stag hunt. If you remember what was the stag hunt and what was the equilibrium in the stag hunt, so the stag hunt game, again there are two players, and each player has two actions to choose from, either to hunt the stag or hunt a hare. There is a single stag in the forest which can be hunted if both the players cooperate and try to hunt that stag only. So if both of them cooperate, they get 2 each. What is the alternative? Alternative is that any player, instead of going after the stag, could go after a hare, because there are plenty of hares in that jungle also. If he gets the hare, he's getting a hare, so it is not bad, but it is not as good as a stag. So suppose player 2, instead of going after the stag, goes after the hare, he gets 1. what about player 1? Well, it is such the case that if the other player is not going after the stag, player 1 cannot alone will be able to hunt the stag, so he gets 0, he gets nothing. Similarly, if player 1 goes after the hare, he gets 1, which is worse than a stag, in which case player 2 again will be left with nothing, he will get 0. And if both of them go after the hare, they will get their respective hares. So this is 1-1. So this is the game, and we have seen that if we apply the criterion of Nash equilibrium in this game, there will be 2 Nash equilibria. One is SS, that is both hunting the stag, and the other is hare, both individually going after hares. This is an equilibrium because from stag, that is both going after the stag, nobody will like to go after a hare, because if one goes after a hare, then that player will be able to catch a hare, but that is worse than getting half of the stag. So this was the story. Now if I generalize this model a little bit and consider that the number of players is, instead of 2 hunters, suppose there are n hunters. All right, and actions as before. Actions as before, either to go after the stag. For each player, this is the case. One can try to hunt the stag, or one can try to hunt a hare. What about the preference? Preference will change a little bit. So it is the case that 1/nth of a stag is preferable to a hare. Now if this is the case, look, this is similar to the 2-player game, because in the 2-player game also half of the stag was preferable to 1 hare. Here n is equal to 2 in that case, but here we are taking the general case where n could be any number, any positive integer. Now here what will be the Nash equilibria? Let us, from this game, 2-player game, if we try to get some hint, maybe we should try for these 2 sorts of profile, where everyone is going after the stag and where everyone is going after the hare. So is it true that in this n-player game, everyone going after the stag is an equilibrium? Let us see if this is an equilibrium. To see that, what we need to do is to see if there is a profitable deviation from this. What is meant by profitable deviation is that from this action profile, can someone deviate and be better off? Now deviation in this particular game can be only of one type, either if everyone is going after the stag, then you can deviate and go after catching a hare. Now obviously this is not profitable, because if one goes after a hare, he gets a hare, but getting a hare is worse than getting 1/nth of a stag, which is happening if everyone goes after the stag. So this is a Nash equilibrium. Similarly, if I consider the other profile, which might be a candidate, everyone goes after the hare. Is it a Nash equilibrium? Again I have to consider deviation for any player. Here every player is similar. So if I consider any player, suppose player I, and he deviates. Suppose he deviates and he tries to catch a stag. Is that beneficial for him? The answer is no, because if he goes after the stag, he will not be able to catch anything, because to catch a stag, it must be the case that everyone tries to catch the stag. So alone he will be getting nothing. It will be a futile effort. So deviation is not profitable. In fact, it is harmful. So that's why this is again Nash equilibrium. So we have two Nash equilibrium. Is there any other Nash equilibrium? So any other Nash equilibrium, is it possible? And the answer is no. Because if I consider any other Nash equilibrium, then how shall that action profile look like? That action profile must have a mixture of S and H. Some players must be going after the stag, at least one player should be going after the stag, and at least one player should be going after the hare. Now if there is at least one player going after the hare, then that means that the other players will not be able to catch the stag, because to catch a stag you need everyone going after the stag. So in that case it is futile for all these other players whose number is at least 1 who are going after the stag. Their effort is futile because they could go after the hare and be better off. So any profile will have at least one S and one H. Since at least one H is there, people going after the stag will get 0, and there is at least one such person. One such player playing S, that is going after the stag, and his action is suboptimal. He could do better by going after the hare. So this is not a Nash equilibrium. This profile that we are considering here, we are thinking about whether this is a Nash equilibrium or not, is not a Nash equilibrium, because that person, at least one person is there who could change his action from S to H and could be better off. So therefore this action profile is not Nash equilibrium. So that is the proof that there is only two Nash equilibria in the game where the number of hunters can be anything. It can be any positive integer. It can be more than 2. So that is it. What we are going to do now is that we can consider another, a little complicated version of the same stag hunt case. Let me tell you the question here. So here is the variant. Let me read out the question first. Consider variance of n hunters stag hunt in which only m hunters, where m is greater than or equal to 2, strictly less than n, need to pursue the stag in order to catch it. There is a single stag. Assume that a captured stag is shared by the hunters who catch it. So this is the setup, that you need not have all the n hunters going after the stag to catch it. If the number of hunters is less than n, suppose this is m, where m is greater than equal to 2, then that will be sufficient to catch the stag. Now, what is the question? Question is that under part A, our assumption is that as before, each hunter prefers the fraction 1/nth of the stag to a hare. Find the Nash Equilibria of the strategic game that models the situation. Let me take you to another sort of game which is similar to some of the games that we have seen. It has two Nash Equilibria, and this is known as a hog-dove game. This is given as a exercise in this PowerPoint. Here is the story. Two animals are fighting over some prey. Each can be passive or aggressive. So, number of players are two animals. Each can be passive or aggressive. So, these are the actions. One can be passive or one can be aggressive. Each prefers to be aggressive if its opponent is passive, and passive if its opponent is aggressive. Given its own stance, it prefers the outcome in which its opponent is passive to that in which its opponent is aggressive. Formulate this situation as a strategic game and find its Nash equilibrium. Let me discuss another game before we finish this lecture. This is known as coordination game. Coordination game is can be thought of as a variant of the Battle of Sexes game. Here again, like the Battle of Sexes game, there are two players. So, players, two people, let us suppose, and like the coordination Battle of Sexes game, they are planning to go either to a boxing match or to an opera house. However, the actions are, though the actions are like this, preferences are a little different. Here suppose in Battle of Sexes, the husband and wife, the two people, differed on which is the better one to go. One player thought that boxing match is preferable to the opera, and the other player thought that the opera is preferable to the boxing match. Here suppose both of them prefer the boxing match to the opera, and both of them want to be together. That is remaining constant, as in the case of Battle of Sexes. So, it is like this, that in OB or BO, the last two, they are not together, so that is the worst possible. For player 1, going to the boxing match together is better than going to the opera house together. However, this is the same case for player 2 also. So, his preference is not different. And the numbers we attach to them will be like before, 2, 1, 0. Then what is the sort of game that we get? The sort of that game that we get is known as the coordination game. So BB is better for both of them, OO is worse, and the worst possible is OB and BO. Now in this game, what are the equilibria? The Nash equilibria in this game, if I examine this game carefully, I will find that there are two Nash equilibria. One is BB and the other is OO. That is, both of them going to the boxing match together is a Nash equilibrium, and both of them going to the opera house together is also a Nash equilibrium. Though there are these two Nash equilibria, it is clear from this game itself that one Nash equilibrium, that is BB, is better than the other Nash equilibrium, which is OO. But does that mean that this OO Nash equilibrium, which is the worst Nash equilibrium, which we defined as a Pareto inferior state, and this is a Pareto superior state, does that mean that Pareto inferior state is not going to prevail? The answer is no. If I follow the definition of Nash equilibrium, of course there can be a stable steady state at OO. Each of the players is going to play O, though they both of them know that this is a worse situation than the case where both of them were playing BB. And this is the reason for this is that I cannot make the other player act according to my wishes. I have command over what I am going to do, but unified action is not considered in non-cooperative game theory, which we are doing right now. So if I know that player 2 is going to play O, then the best possible thing for me to do is to play O. There is no other way, and vice versa. Now, can this situation that we have discussed here, that is a Pareto inferior Nash equilibrium, is this realistic? Do people get into this kind of trap where they are in equilibrium but this is not desirable? And the answer is perhaps yes. If we look into real life cases, we all many a time find situations where people are stuck with actions which none of them wants to take, but still they do because others are taking that action. One could be this, which we call QWERTY puzzle. What it means is that this QWERTY is nothing but the keys of a typical keyboard, maybe computer keyboard or maybe a typewriter keyboard. QWERTY. These letters come on your left hand on the top. Now this kind of keyboards that we use is not the best sort of keyboard that can be devised, can be designed. In fact, when this sort of keyboard was designed, it was to reduce the speed of the typewriters. People who used to type, their speed used to reduce because of this design of typewriters, this sort of keyboards. One reason could be that most of the peoples are right-handed, but in this keyboard the letters which we use most, for example E, A, R, S, all of them come on the left hand. So this is not the best keyboard that can be designed. This is in fact a suboptimal keyboard, but still people have continued to use this keyboard. And why is that? Because everyone else is doing that. So each company which maybe makes these computer machines and keyboards finds that everyone is buying this sort of keyboard. So if I do something else which might be better, if everyone stuck to that better keyboard, everyone would have been better off. But I, as an individual, if I try to do something else, my keyboard may not be sold in the market. So I still stick to the run of the mill keyboard, which is an inefficient keyboard, and which is the QWERTY keyboard. So, the point is that if there is a Nash equilibrium, which is a Pareto inferior Nash equilibrium, there is no way to rule that out as a steady state. It is a Nash equilibrium by its own right. Okay, so we are going to do an exercise on this topic of Stag hunt. This is an extension of Stag hunt. So, let me first write down the exercise and then we shall try to solve this exercise. So, this is the question. Let me read out the question. This is an extension of the stag hunt game, and the question is the following. In an n hunter stag hunt, each hunter has capital K, a positive integer, units of effort, which she can allocate between pursuing the stag and catching hares. Denote the effort hunter I devotes to pursuing the stag by EI, a non-negative integer equal to at most capital K. The chance that the stag is caught depends on the smallest of all the hunter's efforts, denoted by minimum J EJ. Hunter I's payoff to the action profile E1 E2 ... En is 2 minimum EJ minus EI. Is the action profile EEE, where there are n E's, in which every hunter devotes the same effort to pursuing the stag, a Nash equilibrium for any value of E? This is the first question, and there is a second part to the question, which is that is any action profile in which not all the players' effort levels are the same a Nash equilibrium. So, to put the story in a succinct way, there are n players, and what they are choosing is EI, that is effort level that hunter I puts to hunt the stag, and EI is less than or equal to capital K. And we know EI can be an integer, and capital K is also an integer, and EI is greater than or equal to 0. This is their action, and what is the payoff? Payoff is given by the following. So, UI, E1, E2, En is equal to this is the payoff to player I. Now, before we go further, let us look at this payoff function a more considerate way. Here what we are having is 2 of minimum of Ej minus Ei, which means that given the effort levels put by all the hunters, we take up the minimum of those effort levels. This minimum effort level is, let us say, any value E bar, and then player 1's payoff from putting EI is twice E bar minus EI. And the underlying story behind this is that if the minimum level of effort put by all hunters goes down, then the stag might escape their hunt, and in that case they will not be able to catch the stag, which means that the payoff of this particular hunter goes down from putting any effort for the stag hunt. So, that is why E bar, which is the minimum of Ej's, is coming as a positive entry here. As the minimum goes up, there is higher chance that the stag will be caught. And then there is a negative entry here, which is minus EI, and which is quite intuitive. More effort is put on the hunt of stag, it is worse, the hunter is worse off in the sense that he has now less effort level left to pursue the hares. So, that is why minus EI is coming as a variable in this payoff function. So, this is the intuition behind the payoff function. We have to answer two questions. First,
is action profile E dot E. There are n E's in which every hunter devotes same effort to pursuing the stag, a Nash equilibrium for any value of E. So, that is the first question, and our answer is the following, that for all E's, all integral values of E less than equal to k, E is a Nash equilibrium. And the reason is for this is simple. Let us take any arbitrary, such profile, this profile. Now, for hunter I, the payoff from this action profile is, what is the minimum of all E's? It is E itself. So, 2 E minus his effort, which is again E, and which is E. So, this is the payoff that he is getting, any hunter is getting from this action profile E. Now, to say that this is a Nash equilibrium, we have to consider deviations. Now, for any player I, there could be two kinds of deviations. One is putting an effort more than E or putting an effort less than E. So, suppose I puts an effort EI, which is E plus, let us say, x, where x is positive, and then x has can take only integral values. Now, in this case, what is the payoff of I? It is 2 of minimum of all these E's, which is again 2 E minus E minus of E plus x, and which is less than E, right, because this is nothing but E minus x. This is less than E because x is positive. So, that is why deviation upwardly or putting an effort more than the other, what the others are putting, is unprofitable. So, upwardly deviation is unprofitable. Now, let us consider downward deviations. Suppose I puts an effort E minus x, where x is again positive. So, what is I's payoff? So, I's payoff from this new action profile will be how much? Minimum of all this, which is 2 of E minus x, okay, minus of E minus x, which is E minus x, and which is again less than E. So, downward deviation in downward direction is also unprofitable. Hence, E is Nash equilibrium for any integral value of E greater than equal to 0, less than equal to k. So, this is the first part. There is another part, second part, which is saying that is any action profile in which not all the players' effort levels are the same in Nash equilibrium. So, this is the second part. Suppose player I's effort level EI is greater than let us call it E lower bar, the minimum of EJ, right. So, player I is a player whose effort is more than the minimum of all the efforts put by all the players. Can that situation be sustained as a Nash equilibrium? And we have to show that if that cannot be sustained as a Nash equilibrium, then perhaps players putting different effort levels cannot be a Nash equilibrium. So, here payoff of I is how much? It is 2 E lower bar minus EI, right, because minimum of EJ is E lower bar. So, that therefore, we have 2 E lower bar minus his own effort, which is EI. Now, this is UI. UI rises as EI declines. As EI goes on declining, this UI will rise, because we have a minus EI term here. Therefore, I will have a positive increase, I will have a profitable deviation if she reduces EI to E bar, because this will happen. This payoff function is valid as long as E lower bar is less than EI. So, as EI goes to E lower bar, this payoff is going to rise. So, any player whose effort level whose E is more than E lower bar, the minimum, will profitably lower EI. Okay. Therefore, there cannot be a Nash equilibrium where efforts are different. So, the only Nash equilibrium that there can be in this game is where efforts put by all the players are same. So, that is the exercise.
We shall do one example and then close this lecture. The example is the following. This is also known as public goods provision game. What is a public good? Public good is something which has been produced and provided to the public, and I cannot restrict anyone from consuming that good. So, what happens is that suppose there is a road which is not crowded, and in that road obviously if it is constructed everyone can make use of that road, but you need money to construct a road. Now, if I contribute to the construction of a public good, there is no way I can exclude someone from using that. So, here we have a typical case of free riding, that I contribute, but everyone is using that. Of course, I am also using that road, I am getting some benefit out of it, but I cannot restrict anyone from using that particular facility. Now, if that is the case, then will people contribute? Under which conditions people will contribute, or can there be a situation where nobody contributes? So, this is called the provision of public good and the problems related to that. So, question is the following. Let me read out the question. Each of n people chooses whether or not to contribute a fixed amount toward the provision of a public good. The good is provided if and only if at least k people contribute, where k is less than equal to n and k is greater than equal to 2. If it is not provided, contributions are not refunded. So, which means that if I have contributed for the construction, but suppose not many people have contributed, so in that case the good will not be produced, no public good is there, but I am not going to get back the money. If it is not provided, the contributions are not refunded. Each person ranks the outcome from best to worst as follows. 1. Any outcome in which the good is provided and she does not contribute. So, this is the best possible for any person. Second is any outcome in which the good is provided and she contributes. Third is any outcome in which the good is not provided and she does not contribute. And fourth is any outcome in which the good is not provided and she contributes. Formulate the situation as a strategic game and find its Nash equilibrium. This is public good game. So, players n in number, actions. What are the actions? Either to contribute or not to contribute. So, contribute, let us call it C, and not contribute, NC. And what about the preferences? Well, this is the interesting part. First option is that I am free riding over others, that is other peoples have contributed, the public good has been produced. So, there is the number of contributors is more than or equal to k, there is no dearth of contributions. but I have not contributed. So I am getting some benefit without contributing anything. So C, that is I have contributed, and let us call this P. P is standing for public good is provided, that is number of contributors is greater than equal to k. So this is the first outcome that I shall prefer. This is the best outcome for me. So we are more or less running out of time, so I shall finish this lecture right now, and we shall discuss, we shall pick this problem in the next lecture. So that's all for today. Thank you.
The first question is, in stag hunt game, if both players are worse off in a Nash equilibrium, why does it remain an equilibrium? So the basic idea of Nash equilibrium is being questioned here. So in stag hunt, let us remember how does it look like. There are two players, 1 and 2, two hunters. If what is being asked is that suppose there is a Nash equilibrium which is Pareto inferior, where both players are worse off in a Nash equilibrium, then why does it remain a Nash equilibrium? So we have a Nash equilibrium here which is HH, payoffs are 1 and 1. It is here the players are worse off than say STST, where the payoffs were two and 2. But still this is a Nash equilibrium by its own right. Why? Because go back to the very definition of Nash equilibrium. As long as player 2 is playing H, right, as long as 2 plays H, best action for 1 is to play H and vice versa. So though here both players are worse off, it is a Nash equilibrium. Consider an n player stag hunt game. If 1/n of stag is preferable to a hare and n hunters are required to hunt the stag, what are the Nash equilibria? So n player stag hunt and n are needed to hunt the stag. What I propose is that following are the Nash equilibria. This is a Nash equilibrium and this is also a Nash equilibrium, and in all 2 Nash equilibria. The reason is that if everyone goes after the stag, there is no reason why any individual player will go after the hare, because one hare is worse than 1/nth of a stag. So that's why this is a Nash equilibrium. Why everyone going after the hare is a Nash equilibrium? Because from here, if anyone starts to go after the stag, she will not be able to catch the stag, so she will get 0. Here at least she is getting 1 hare, which is better than getting nothing. So both are Nash equilibrium. Is there any other Nash equilibrium? No other Nash equilibrium. Why? Because in any other profile where at least one player is going after the stag, right, there could be more than one players going after the stag. In such cases, the stag will never be hunted because you need all the n players to go after the stag, but that is also ruled out because this is taken care of here. So, the number of stag hunters is here more than 0, but less than n, which means that these players who are going after the stag will not be able to catch the stag. So, it is better for them to go after the hare. That is why any other profile is not a Nash equilibrium. Describe the hog-dove game and find its equilibria. The hog-dove game is the following game. I am just drawing the payoff matrix. As usual, there are two players and their actions are being aggressive or being passive. If both of them are aggressive, they get 0 0, both of them passive, they get 3 1. If both of them are passive, they get 2 2. If one is aggressive, the first player is aggressive, the second player is passive, they get 3 and 1, and vice versa. What is the Nash equilibrium here, or what are the Nash equilibria here? There are in fact two Nash equilibria here. One is aggressive passive and the other is passive aggressive, that is this and this. You can check that there is no profitable deviation for either of the players from these two equilibrium profiles.